folks, Assalamu alaikum. I'm Muhammad Shahriar al Muslim Mithul. So, earlier you have learned the basics of linear algebra, basically some basics about tensors, scalar, vector, array, and so on. Okay, so we'll start from obviously what we have left on. So, earlier we have talked about scalars and others, so we'll just review that a bit. So, as a whole, you can see that tensors are mostly like tensors have various type of stuffs. One of those are scalar, one of those are vector, one of those are array, and one of those are high dimensional one. Which now how do we understand that, right? So okay, let me just add this one. Okay, here's the factor, right? So if you just look into this, what we can see here is tensors. So starting with 3, for example, if we had a value 3 or something, we are just recapping, okay, just to be sure what we are talking about. Basically, we have talked about this concept earlier, so if you haven't checked out the video, just feel free to check the video in the series. You can just understand it from the scratch. Now talking about this, so 3, right? So you can see that the number 3 as a whole, if you are adding it or if you're just writing it down, like for example just 3, right? Just a value, just simple value. This actually doesn't have any dimensions with it. Now talking about the vectors, we earlier mentioned that the vector generally does have one dimension, right? So the dimension was actually meant by this, like for example 3 4, okay? So something in array, so the 3 4, if you talk about, if you assume this as an x-axis, right, as x-axis, so in the x-axis you can see 3 and 4, right? So these two values can be presented in an array, something like that. Now talking about the actually the array, which we sometimes call matrix and so on, right? So what happens is, it's for example, if you have 3 4 8 and 2, so this 3 4 8 and 2, just check this out, what happened here. This 3 and 4, this value or this vector, we've just inputted that here. We've added that for sure, no issues, but we have added one more, which is 8 2. So this 3 4, now we are just considering this 3 4, and I'm just saying like these 3, okay, these 3 and these 4 values are actually part of x-axis, no issues, but these 8 and 2 are part of y-axis, no issues, okay? But now as we have 4 values, now we can represent these in 2-dimensional values. How? You can see in x-axis we have 3 and 4, no issues. In y we have 2 and 8. So as a whole, we can say that there might be a point like this 3 8, you can see 3 8, so this is a point, this is a point, so A, and there is another one which is 4 2, okay, so this can be another 2. So using array, we can now present a value in a two-dimensional set, or whatever you call it, okay, in 2D dimension, okay? So it has both x value and y value for a particular thing, okay? So this is how we actually mentioned about the dimensions as a whole. So you just need to understand by the value, nothing else. We don't need to complicate that. You can see 3, it does not belong to, or you can't get any other clue from 3. So you can say, okay, it doesn't have any dimensions. For the vector, you can say 3 4. So assuming that respective from the x perspective or from the respective x-axis, it has 3 units from it, right? You can see if it's starting from maybe 0, 3 and 4, and no issues with that. And in array, you can see 3 4. Obviously we can assume that these are values in the x-axis and these are values in y-axis, so they do represent as a whole like something, right, for sure. So we can see that, and it has 2 dimensions right now. So this is how we do understand the dimensions, okay? So let it be. If you have any confusions around it, feel free to ask in the comment section as well. So Okay, now let's start our main topic today, so which is matrix multiplications. So what is a matrix? So as a whole, you have just seen a moment back, which was our array, right? So this is basically the matrix representation as a whole, but it does not it is generally not a square matrix in general. It doesn't need to be. So what do I mean by this square? So for example, if you have 1 2 3 4, sorry, 3 it doesn't seem to be like 3. Okay, 1 2 3 4. So you can see you have just understand the row, you have two rows, right? What is that? Row 1 row 2. So you have two row, no issues. And then you have two columns, one column, two columns, right? So this is totally, you can see exactly the same value, right? So these are basically square matrices. Okay, but here if you just look into that, here we can see we have 1 2 3 three rows but two columns, which we can call as three rows, right? 3 into two columns, 3 into 2. Okay, this is how it works. Now talking about matrix multiplications. So something, if we represent in a matrix format, and if you want to multiply, there is some rule. The rule is, if you see the if we have A matrix to multiply with B, the column of the A matrix, columns, a number of columns we have in A matrix should be similar with the number of rows we have in B matrix. That's very might be tricky for you, but okay, let's get started. We'll just see through this example. Okay, so here you can see this is our A matrix, okay, and this is our B matrix. No issues with that, right? Then how can you, and that is the rule to go for the multiplication. If that doesn't fit in, we can't even multiply, and so forget about it. Now I'm just going to check this one. If B has as we were looking for, you can see this is row, this is column. We have three rows, 1 2 3 and two columns, right? So three rows, two columns. So we're looking for here from B matrix that if it has two rows, at least, because two columns, we need two rows and one whatever it is. The other thing is not something we bother. So here you can see we have two rows, right? And here we have one column. So the rule is we have to look for these two, if they are similar or same or not, right? You can see, yeah, they're same, 3 into 2 and 2 into 1. So yeah, if that fits in, we can multiply them. Now how to multiply them? That is something tricky as well. So the thing is, you can see we have 3 4, right? Have 1 and 2. So what happens is these two gets multiplied individually, like 3 gets multiplied with 1, 4 gets multiplied with 2, and then they adds up. This is the rule. Okay, so let me just this one so that you understand. So let me just remove these ones. Okay, great. So here let me read it again. So here you can see that these three, as I mentioned, this is how things work. So 1, okay, so we can see this is how it should work. 3 and 1, first 2, 3 into 1, then we add with 4 into 2. Okay, then done. So now talking about the second one. So if you just do it for this one, so 5 into 1 should be 1 plus 6 into 2. So this is how it works. You can see 3 into 1 plus 4 into 2, 5 into 1 plus 4, 6 into 2, and so on. Okay, and then we just sum up the things. You can see you have summary. I have to add these things up. So after the adding, we can see we have this thing. We have this array. Now here is an interesting factor we will see. What's the interesting factor? If we just remove these, and I've just mentioned the process, right? But I'm just going to write the dimensions. Here you can see we had 3 rows, 2 columns, right? Here we had 2 rows, 1 column. Interestingly, the output is we have 3 rows and we have 1 column, right? You can see, and from here I believe this um, I mean the dimension, okay, just like cross. Okay, okay, great. So here you can see we were looking for this law, like this two values should be same. Okay, no issues, it fits in. Now the remaining two is actually the dimension of the output. You can see 3 and 1, right? Great. Now why are we learning these things and so on? All of these questions are going to be answered, I believe, gradually, right? Why? Because today I'm not going to cover some interesting factors or applications about eigenvalues and vectors. I'm not going to cover those, but I'm going to cover what they are, how to or what's the impact on them, and the applications on ML and others we will cover in the next video, which will be the last video on our mathematics for machine learning series. Okay, so okay, but if you go for that part, and then you will start understanding, okay, this is why we started learning these parts, because at the end, whatever we're doing, like if you have ever worked with machine learning models, that we basically input CSV format data sets or whatever it is, we just put some sort of input, and then we do make modifications to it so that we can make them something like an array, and so then the multiplication and other does happen. So at the end, it is actually arrays and others, eigenvalues, vectors, and so on, that is actually going running in the backend of machine learning. So that is one of the reasons we're learning these things. Okay, but yeah, when we are solving problems, or when we are using the machine learning model, for sure we don't actually do these things manually. We have a computer for that, and we will see some things, especially the coding part. Okay, now let's talk about this one. Here we have, interestingly, here you can see we have 3 rows, right? 3 rows. Okay, let me just use a different color. We have 3 rows and we have 2 columns, no issues. Here we have 2 rows and 2 columns, no issues. So as we can see, these two are same. So okay, as these are same. Okay, so that means we can have matrix multiplication here, no issues, and the result should be 3 into 2 then. And you can see exactly this is 3 rows 2 columns. That's good, right? So now this is totally up to you. You can I hope you understand the process. You can see in here, what should we have? We should have 3 into 1, then what, 4 into 2, and then we should add them up, right? 3 into 1, 4 into 2, right? Great. But interestingly, this time we have another column here, so the process should be same. Again, the process is 3 into what, 9, 4 into 0. Again, if you just look into here, the earlier one, so we had this thing 3 plus 8, right? This is the one, right? And we had this space, and then we had this one. Basically, what's happening, you can see we had a value or column of values, right? No issues. So we will basically, first of all, we'll do all of the stuff for this column, and we'll have 11, 17, 23, just like that. Then we'll just deal this part, or sorry, 90, just like another column, and we'll just deal with this, and we'll get another column. That's it, simple as that. You just don't need to complicate these things and process. Okay, it's totally the process or the practice which will make it easier for you. That's it, simple as that. Okay, yeah, that's totally normal. So we have 3 rows 2 columns. Okay, we have 3 rows and 2 columns, no issues. Great. Now let's talk about something which is this, which I believe you have seen this earlier as well. This was part of some sort of house guessing algorithm or whatever you can call it. So assuming that these are the prices, okay, for any house. So we have 1 to n, so n number of houses prices here, and there are some features, especially like x is 1.1 or 1,1, whatever it is. So these are basically the position in the matrix, to be honest, okay. So how, if you just look into, as I mentioned earlier, something I believe I have shown you these things earlier as well. So just assuming this is a matrix, and now x, y, z, sorry, I should have x for all of them so that you understand it properly. X and x and x. Okay, so here for this one you can see it's part of this is row 1, okay, and row 2 it is column 1, column 2. Let me just add this part, C2. Let me just do it C2, and this is row 1, R1, row 2. Okay, so we can call it as the convention is row and column. Okay, this is how we to understand the process. So here the row is obviously 1 and the column is again 1. Okay, so this is what it is. Okay, and talking about this, so you can see the row 1, column 2, row 1, column 2, 1, 2. This is how things working, and you can see exactly 1, 1, 2, and so on. This is how it works. This is how things work. So if it is a huge matrix, obviously it will have lots of data. So this is, we are understanding this as a matrix. Okay, and these are the values, basically the result, or the price of the houses, in number of houses, and it depends on multiple things, and depending on that we have just formed some equations. Here you can see these are some sort of features, maybe as I mentioned earlier, maybe it's a distance from school, road, and so on. These are the features. Okay, and we have some constants. So the goal is, we know these features, these do vary. Things that vary is basically some sort of features, right? So, and we have some constants. So we will just solve this matrix and we'll get these values a, b, c, and m. So what's the goal? The goal is, now if someone comes up and say, hey, this is a house, and I have like features from this to this, and now here you can see the features from this to this. What does it mean? Here I've just mentioned x I comma 1 to x I comma m. So what does it mean? It means here you can see I can have lots of values, right? So when I is 1, so it is y1, y1, and obviously I comma 1, so it is 1 comma 1. So that's the thing, it's basically meaning an equation, particular equation. So if you have lots of equation, like from if we have specifically for example, if 29, if you want to look for, there is a house which is house 29 for example, and it has lots of features from like, and the features are 29 1, x 29 2, and so on. There are lots of features, and basically they have some values. Okay, like distance from house, distance from this. Okay, we have lots of them, 29 comma m. So we have lots of features. So basically the goal is, when we solve this matrix, we got some value, these constant values a, b, c, and m. So now we will just easily use this equation, right? A plus b, and we'll multiply x 29 comma 1 with b, and then it goes on. Okay, this is the process. Obviously this is not exactly how we should, obviously the process is same, but yes, I'm not doing anything, I'm not solving the problems from scratch and so on, but this is how we do it. We just get the constant values, and then we'll just use it whenever we have we are provided with any kind of features. So we can easily say, okay, this is the price of the house, this should be the price of the house. Now the user case is simple. User case, let me just talk about the user case. That is, you live in US, okay, and here is your friend in BD Bangladesh, and what happens is he basically deals with lots of houses, right? And he has a database, and what he has done is he has basically computed or analyzed the data, and he now knows if someone just tells him like, okay, this is the distance or from road distance from school and so on for the particular house, he can easily guess, okay, this should be the price, this should not be more than this 500k, for example, something like that. So that's the thing. So you just have talked with your friend like, hey, I want to buy a house and these are the features I do have, can you tell me like what should be the price? You said, okay, the price should be y equal 500k, depending on what, because your friend earlier basically had analyzed the data and got the values of A, B, C and M. But the thing is, it is not A, B, C and M. In general, there can be lots of constant here. Just for an example, you can see A, B, C, there can be much more. So it's just for the example, okay? So just I'm meaning A, B, C and M, for example, or something like that. And then you provided the features X, Y. I should not mention Y because this should keep it same, just like 29,1 to x29m. Okay, you just provided these features to your friend. Hey, tell me the price. He said, hey, this should be the price. Then you went to the broker and said, hey, give me the home within this amount, okay, because it should not be much more than that, right? This is how we actually started solving the real world problems, right? Analyzing the data trends and so on. Okay, so how would your friend solve the problem? Now here, if you just look into this, or how would your friend analyze the data? Your friend could easily create an array which could have all of the house prices. Then there could have been another array, this, which will have the features, and there would have been another array with the constant values. Easily, now you can say, how did we form this one? Now you can easily understand how it formed. As I mentioned earlier, how do we work with the matrix multiplication? You can see easily if we just do this, what do we have? A and 1, then plus, then this one, x1 comma 1, then b, then this one, it adds up, right? See, x1 comma 2, then and then m x1 comma m, right? So exactly, and obviously it should be equal to this. You can see each corresponds to a particular value, you can see. So it should be y1 equal this. And if you just look into the earlier equation, isn't this the same thing? y1 equal a plus bx1 comma 1 and so on. Isn't this the same thing? So this is how we can represent in the matrix multiplication format. So yeah, this should be the format, and this is how we should use it in mathematical and in the coding format. Okay, now another important factor, another important thing which we need to know is symmetric matrices. Okay, so symmetric matrices are basically the matrices which are square. Here you can see, how do we understand square? We have 3 rows, right? 3 rows, and we have 3 columns. So we have 3 columns, so it's a square. Okay, that's how we do understand. First of all, it has to be square, a matrix has to be square, and if this is the matrix which is X, okay, and if we get the transpose of it, what does it mean? Transpose, what do we understand by transpose? Okay, let's understand what transpose means. So here we have 0 1 2 1 7 8 2 8 9, right? Great. So we have these values in first column. Okay, this is totally X. But talking about transpose, in the transpose matrix, what should we have? The first column in X should be the first row in here. just forget about these things. I don't think I do have these things. Okay, just assume that we don't have these values. Just assume that 0 1 2, right? We do have 0 1 2, right? So what will happen? Transpose is basically from column to row. This is something like that. We have this is a column, right? We will just make it a row. 0 1 2 transpose. That's it. Okay, from column. If it's in a column format, we'll just take it to the row format. 0 1 2, it became 0 1 2 in this format. No issues. Then I will just remove this part. Okay, so yeah, that's the thing. This is how we are doing the process now. 178 as a whole, so this is in a column, so we should just put that here in the row. 178, done. This whole column has been taken in the row format from column to row. Okay, just remove these things and we can now easily see what's happening here. The final column we have here is this one, 289. So this should be 289, right? And now if we just look into that, we have x transpose. So if you just check the similarity, you can see 0 1 2 0 1 2 178 178 289 289, right? So this is basically got symmetric matrices. Okay, now in machine learning we basically deal with lots of things which might be something like that, and we'll have some benefits of it. We'll learn about it later on. Okay, now let's talk about the identity matrix. Okay, so if a matrix, it can have, obviously matrix can have lots of rows and column, no problem. Here we have 1 2 3 4 rows and we have 4 columns, no problem. So here you can see symmetric matrices. So identity matrix A is a matrix which is first of all a symmetric matrix. So what is a symmetric matrix? As I mentioned, it has to be squared, so you can see 4 into 4. Then the transpose of the matrix should be same as arrays. Like for example, if it is x, then x should be x. X should be equal to x transpose. Okay. Okay. Here, this matrix, if you have some sort of value, if you just look for this thing, you can see. Okay, if you just use the transpose, you can easily get the exact value. So that is it. And if you are not sure, you can just check this out. You can pause this video and just verify. Okay, so it is a symmetric matrix for sure, first of all. Then after that, what has to be done? That is, every element along main diagonal is 1. So this is a main diagonal. Okay, this is the one in the middle, so it should be 1, and you can see every element here is 1. Great, every element here is 1. Then all other elements are 0. All other are 0. Good. Then we can represent it just like this notation, I and this, and this here, I and then n. Okay, so this n is basically the number of rows and column or whatever. Here you can see this is how you can understand, like here the row and columns are same, so this is actually the 4, right? This is what we are going to present. And now you can say, okay, is it either row or column? Actually there is square matrix, right? So it should be same. So is the value, just any value, you just pick it up. So this is L4, sorry, I4. Okay, so this is how we can represent an identity matrix. Now the question is, when are we going to know its application and so on? We'll see. Like to to get the eigenvector and so on, we will just use this kind of things. Okay, now matrix inversion, that's an interesting factor. Okay, now the matrix inversion is because now you see what happens in real life. So some of us have, like when we were doing some division, like for example, x equal to what should do to y, okay, plus something 1, and then we just minus this one from both of the cases, x minus 1. Okay, we just for example we're just looking for when to get the value of y. Okay, what's the value of y? Okay, so first of all we just eliminate minus from both of the places, so minus x minus 1 equal 2y plus 1 minus 1. Okay, then we end up with x minus 1 equal 2y, right? Then what do? We divide 2 from both of the sides, right? X minus 1 by 2 equal 2y by 2. This is the process. This is the real process. Okay, then we end up with y equal x minus 1 by 2. Now here in the process, when we were doing this thing, you see this part here, we have x minus 1 and it is divided by 2, which we can write like this, right? X minus 1 into 1 by 2, right? And in the right side obviously same, 2y into 1 by 2. So what's this, right? Is basically the reverse of 2, right? 2, this one, to the power minus 1 or reverse, whatever you can call it. So this was in mathematics, simple mathematics, we just divided it by that. But when we will have some cases like we'll have matrices in both of the side, matrix, and so on, and we have to like divide something, and will we just divide the matrix? No, we can't do it. We will then use the inverse of it, right? So these kind of things, this is and we'll just multiply inverse in both of the sides and so on. Okay, so this is one of the reasons we need to learn the inverse. Okay, so I believe you understood the process, because obviously we're now learning the mathematical or whatever you call it. We are just now learning to do calculations within the matrix or with the matrix. Okay, here you can see what should we have. The matrix inverse of x is denoted as x inverse, and this is the interesting part, the identity matrix. So I've just learned here. So if we have a inverse matrix inverse of a particular matrix, which is x for x, like for example we have this x matrix, and x inverse is the invert format, inverted matrix, and if we just multiply them, we will end up with an identity matrix. Okay, that's that's where the significance of identity matrix comes in. Like it helps us to understand, like, okay, if these things actually are correct or not, because sometimes you want to verify that, right? Like someone just said, hey, this is the inverse of this x matrix. You have been provided some sort of matrix, and you have a matrix, right? And then you will just try to have the multiplication. You'll say, okay, yeah, we are just getting the inverse matrix, so yeah, it's perfect. So these kind of things. But to be honest, whatever I'm saying, this is basically adding up. Whatever I'm saying, whatever I'm doing, these are going to add up, and we will see that every time we're introducing a new concept, a new thing I'm mentioning, we're just using the earlier concept I mentioned. Okay, so that's the thing. Okay, here matrix inversion. So earlier we did mention about this case, right? I did mention about this case, and we were talking about this, right? Like, hey, this is basically the house price and the features and the some parameters, some constants. Okay, so from here, as mentioned, your friend, I mentioned you are in the US and your friend is in Bangladesh. So your friend is supposed to like calculate these parameters in Bangladesh, these constant values. So how will he or she do it? Obviously, you can see there are three metrics. Obviously, there should be these kind of stuffs like adding up, inversion, and so on. So this is the process. This is how we can solve the problem. Let's just now dig in. Okay, so assuming that this whole matrix, this is a value, right? Obviously, this matrix within that there is a column. There is one column only. There are multiple like n rows, and we have one column, right? And we can just call it y. Okay, the whole thing we can just call it y matrix, whatever it is. Okay, and this whole thing we can call it as a X matrix, and this thing we can call it W. But what's the dimension of it? We have, we're not sure about the dimensions or number of what do I say, rows we have here, just assuming it's m number of stuffs, okay, and the column is obviously 1, and here we have how many rows we have here. So we have columns, m number of columns here, you can see, not m number directly, m plus 1, you can see 1 to something m, and then we have just 1 also, so something like that. So these, and now we can say, okay, are they adding up, or so I'm just assuming the dimensions, okay, this is not exactly how it is supposed to be, but I'm just assuming some sort of, okay, this we have m and plus 1, obviously this is our column, and the row is I believe n, right? Okay, so we have n row and some sort of m plus 1, I'm assuming. Now you may ask, hey, is it why they are not same, why something like that? I'm just assuming totally. It's not a mathematical concept, it's totally an example, okay? If it is, if it was a value which is equal, obviously if it was a value which was supposed to, or if we had two matrices which was supposed to be multiplicated here, it would have been the row and column should be same if we would have to do it. But if it is not there, then we can never ever actually multiplicate them. So just I just try to show the dimension, but yeah, let it be. It's not clear, to be honest, because it can vary, right? Okay, now just assume that this whole thing is X matrix, this whole thing is Y, sorry, W, this whole thing is Y, okay? Just remove these things as a whole for now. Okay, so Y equal XW. Now the thing is, this can be the equation. So how can we solve this thing? So here you can see how we can solve is, this is the equation, right? Then at the both of the sides we can multiply it with X inverse. You can see this, okay? And then, as we know, now let me just write it so that it's easier for you. Okay, and then the both side, now I'm just trying to add one thing, which is X inverse. So X inverse in the both of the sides, we are just multiplying with it. Okay, great. Then great. So, and now we know X inverse and X, if we just multiply them, we should end up with an identity matrix, right? Here we have seen that, right? Great. So should have I, identity matrix, and W, and then X inverse Y. Great. And basically identity matrix, to be honest, if you want to identity matrix as a whole doesn't carry that much of weight. How can you understand? Basically I into W or is basically W as a whole. If you just multiply them, you will just end up with W. Okay, that is it, whatever. Now for example, if you want to confirm, so if you have 1 1 0 0, this is an identity matrix, but it is I2, because you can see that we have 2 row and 2 columns. Okay, no problem. Now what right? Now whatever we want to multiply with this, for example, maybe we have 3 2, it seems like a vector, but let me just make it a bigger one, which is multiplying it. Obviously I need to also think about the thing. At least we need to have, this is, we have 2 row and 2 column, right? So column, right? So we at least here we need to have 2 rows. Okay, 2 rows. Okay, so for example 5 6 7 8, oh sorry, 8 for right, right. So here we have 2 rows, 2 columns, again 2 into 2. Okay, now if we just multiply them, okay, although it's an identity matrix, okay, if we just multiply them, you can see what will happen. So sorry for the first rows, okay, so 5 into 1, okay, and plus 6 into 0, okay, great. Then same thing happens with these two, 5 into 0 plus 1 into 6. Then same happens for 7 into 1 plus 8 into 0, and then I believe this is 0, yeah, 7 into 0 plus 8 into 1. So what we end up with is 5, 6, 7, 8. Okay, so whatever you multiply with identity matrix, now you see you can so that's why we can write W equal X inverse Y, right? And W basically A is the matrix which is what your friend was looking for, the constant values. So how can he get the value? How can he get the values for the constant values? He can easily get from this equation, X inverse into Y. This is X, this is Y. So if he just solves the problem using X inverse Y, he or she can easily get the constant values. That's it. And then you will just mention the features and you will just multiply with it. That's it. You can guess any, and you can know about any house price existed maybe in a particular area, and it depends on the data, right? Okay, great, right? So this is how we can do it. We can solve the problem. So I believe you have seen the concept of inverse matrix. You have seen the concept of symmetric matrix. You have seen the concept of what not. Okay, now if you just look into a real world problem, for example, just assume that this is a house price which is 4 crore, for example, and this is a feature, maybe this is 4 kilo the house. Okay, just let me just draw it. And there is a school, okay, and there is another house. Okay, this is how we solve the real world problems. And so okay, the distance from this house is 4 kilometer, and for although it's not realistic minus value, just assume that, okay, for example, you're just assuming, okay, the distance from this is minus 5 kilometer. Although if it doesn't exist in real life, if it was a house price, it should have been 5 or something, okay, but I'm just assuming just for an example. Okay, great. So it's the distance from the school for the houses. Okay, it's house 1, it's house 2, and there might be another factor which is road. Okay, from the distance from the road for this house is 2 kilometer, just for the sake of example. And let me see, let me give it a road or something like that. You might sim this as a river or so. I can consider that as a river as well, no issues. And we're considering it as minus 3 kilometer. Okay, from there. Now this is what it is. If you know the value of B and C, obviously you will get this easily. So that is basically how we get the B and C from solving this X inverse Y. We get B and C, and we can easily get 4 crore and so on. But if not, if we don't have that one, then how do we solve it? A lot of things that comes up. Okay, so I'm just trying to make you understand, okay, how things work. Okay, so now let's get back to the problem. So just assume that we don't know the value of B and C. Okay, we just don't know the value of B and C. We now want to know the value of B and C. Okay, here you can see we have features 4, 2, minus 5, minus 3. Okay, so we have this 4. Okay, now you may ask, hey brother, we had 1 out here, why is it gone? That is the interesting factor. That is actually only for this particular problem, which is here, we had somehow created, or some scientists mentioned, okay, this should be alone like added to the equation, and you may consider these as x to the power 0, no issues with that. But some scientists may have just proposed this equation. Just assume just like that. It was mentioned this should be the equation, and then you just calculated the thing. Now here in another area, another scientist mentioned, hey, no, you just don't need to add this up. This is the easy simple equation. This is the equation. Just find out the b and c, and then you are good to go. That's it. So you just found out 4 2 minus 5 minus 3. It totally depends on the equation formation. There is nothing you need to be cautious about. Okay, there is no one or so. You just don't need to bother about it. This is actually we don't bother in machine learning as well. Okay, I'm just trying to make you understand about the how things to work if there is an equation. Okay, just understand. So we have 4 2 minus 5 minus 3. So we just create a matrix here, 4 2 minus 5 minus 3. Okay, and like that, just like that, it creates an x matrix. Great. And then these two creates another matrix which is y. Great. And then we know w, which will have the constants, which is b and c should be equal to this x inverse y. So what we have to do, we just need to find, we have x, right? We have x, right? This is our x and this is our y. Great. Now what we have to do, we just need to have the value of x inverse and then y, and then multiply them, and we will end up with two values, some sort of two values, and these two values are going to belong to this. One will be for b, one will be for c. That's it. Now you can ask, how can we get the x inverse? This is totally, there are obviously there are lots of process out there. We can just follow that. You can just look for any YouTube videos out there. You can check this out. But in our coding, we don't even need that. We just need to know what we need. That's it. If in NumPy, if you're using that or any other coding language, you will just mention, hey, give me the inverse. That's it. It will just give you the inverse. That's what we're bothering. I'm just not going to show you how to get the inverse value, because that's going to be, if we go for that, for every concept, it will take a long period of time. Okay, let's just avoid that. And I'm assuming you will just do go to YouTube and look for how to get an inverse function, inverse matrix. Okay, great, that's the work. Now let's talk about when can we have actually inverse values and when we can't. Okay, when a matrix is not singular, okay, but can only be calculated only if the matrix is not singular. Okay, then all columns of matrix must be linearly independent. Okay, so what does it mean? It means, okay, when can't we actually calculate and don't calculate, or we can't calculate the what I would say, inversion. Okay, so for example, if we have a matrix which we have 1 2, the values basically we have the value 1 2 2 4. Okay, if we have this kind of values, what's the issue? Okay, what's the issue? If we have 1 2 2 4, you can see what's happening here. 1 2, it's row 1 row 2. So here you can see that 1 2 4 is actually the multiplication of 2 with 1 and 2, right? So it is basically singular. So what do we mean by singular? That is what? Let's just look into this equation. 4b plus 2c4, right? If like using this 4b plus 2c equal 4 minus 5b minus 3c equal minus 7, right? What we got? We got this one, which was 4 2 minus 5 minus 3, right? But if this is a matrix, just assume that, okay, this is the matrix provided, just been asked to form the equation. What should we have as an equation? We should have 1b plus 2c equal maybe 4, and we should have 2b plus 4c equal maybe minus 7. Yeah, okay, just like that. Maybe we have been provided the x matrix, just got the equation. Now you can see that what we are saying is we have do we have two equations here? That's the question. That's the issue. We don't have two equations out here. So here we have seen earlier that if the slopes are equal, okay, and there is a gap between them, we never have a solution. We have to collide at a certain point. And if the slopes are equal and they start from same point, then they again have infinite solutions. So actually these two, if you talk about that, these two are actually the same. But in real life, although I have made it up, but it should have been something like 8, okay, if I've been provided this. So you can easily see that okay, this equation is basically the multiplication of 2 with the equation 1, like 1b plus 2c equal what? Obviously 2 into 4, right? Exactly the same. If you have just exactly the same, like how can you get a solution? Is basically you have infinite same thing, right? Isn't it? So as we can't do it, as you can easily understand that these are the same. When we have in a matrix, we have bracket 1 2 and 2 4, you can see this row can be achieved through the multiplication of 2 with this, or whatever it is multiplied with. Then it is not obviously it is yeah, it's basically singular. Then it is singular, right? Let me just remove this and make it easy for you. Okay, so exactly is basically the same thing, right? As mentioned, it might be ab plus 2c equal 4 and 2b plus 4c equal 8, something like that. So it's exactly the same thing. Then why, if the equation is exactly the same thing, obviously there is no meaning of you will going to get a common value or some point where they will collide. It's basically going to be something like that. So yeah, that's when you cannot get a inverse function. Okay, now the question, or now the work for you is you just have to find out why not, why can't I do that. Okay, that's totally your homework. Now let's look for another thing. Can also be calculated if. You can also calculate it, like it doesn't need to be all the time the square matrix and so on. There are a few laws here. Here you can see that if in a matrix, this is a matrix, right? We have what? We have 2 rows and 2 columns, right? Great. So the number of rows as a whole, number of rows, right? Number of rows, right? So if you just represent this in a graph and so, or you can say the dimension, basically these two dimension basically means 2 columns. Okay, the columns, we have 2 columns. Okay, great. Great, that's why we have created 2 1, no issues, 2 dimensions. And talking about the row, the number of rows we do have is what we do present in as a line. Okay, so here you can see when we had 2 equations, we just provided them here. Obviously we have, or 2 rows. Okay, here you can see we have 2 rows, so we have these are exactly same. Let me just give this example: 4 2 9 5. Okay, let's just focus on that. I'm not sure about what the slope is currently here, but it depends on Michael mx plus a, so we just have to let me just say we're not bothered about slope, because earlier we have showed or you have seen how we got the slope. Okay, that was for a particular problem. We have just copied that thing, that image, so we don't need to bother about slope, and so we just check out like the line, assuming that this is the line. Okay, we have you can see we have 2 columns, right? 2 columns, so that's why we have 2 dimensions. Great. Then we have 2 rows. That means and if they are not exactly same, there should have been two type of 2 lines. Somewhere maybe they would collide on somewhere, somewhere they might not. Okay, but if we have same equations out there, then there should be just, or if there is just only one equation, there should be just only one line, right? Right. So this is what happens here. You can see, as they're exactly the same, we can call, okay, there is only one equation actually. There is no meaning of adding two, so just a duplicate. So if there's one, then we'll just add one line, and it can be however it is. So this is the case. Now this is what we have here created. So matrix is square if number of row equal number of column. Okay, n which we understand by here as a whole. Maybe this you can call this here. You can see two lines, and two columns. Obviously, two columns represent two dimensions, two axes, obviously, and these two represent the rows. Okay, no issues with that. Or this is not exactly the value we do come in. We can just present, okay, how many lines we should have. We can understand by the number of rows, and how many dimensions we should have. We can understand by the number of columns. That's it. That's totally an observation. Simple as that. So here, from here, we can say we have 3 rows and we have 2 columns in a matrix. I don't know the exact matrix we do have, okay, but there should be 3 into 2 format for this particular one, and for this one we should have just one, right? So one row, and we should have column, right? We should have 2 columns, just like that. One row, 2 column, 1 2, right? Okay, now so matrix is square if n number of row equal number of column and so on. Okay, but it basically averts over determination if number of rows is greater than number of columns. So here number of rows is greater than number of columns, obviously 3 2, so 3 is greater, and averts under determination when number of rows is less than number of columns, something like that. So these are the things we also need to keep it in mind. Okay, let's just move on from here. Let's go for diagonal matrices. So from now on, it should be pretty much easier for you. Diagonal matrices, I'm not going to look into these text. So you just can pause and read this out. You can easily see there is non-zero elements along the main diagonal. Obviously non-zero elements. It is not saying there should be only one. Is in the identity matrix, in the main diagonal there should be one only, but in the diagonal matrix they are basically happy if there is any particular value. It can be -1, -3, 4, 5, whatever it is, they are happy with it. So that means diagonal matrix is in the main diagonal if there are some value except 0. Obviously zeros, we are not expecting zeros here, but zeros everywhere else, but in other places there should be 0. So we can call this as a diagonal, like 3 4 0 0, because here this is the main diagonal. So here you can say 3 4. Okay, but we cannot call it an identity matrix. We can call it an identity matrix if we have 1 1 and then 0 0. In the main diagonal there should be only one, then it is identity matrix. That's it. So this is what it is. And now the factor is, you will ask why the diagonal matrix is important, so on. We'll see later on. We'll get to know about it. Okay, now let's talk about orthogonal matrices. Now this is the interesting factor. Earlier we have seen this thing, right? In the 2 dimensions, in our x-axis and in our y-axis, assuming a unit in here, like this is 1 obviously, right, and this is 1 here as well. So a particular unit, if you take in the x-axis here, for this one we should have the value for here is x value should have 1 and y value should be 0 1 0, and for this here should have 0 comma 1, right? Isn't it? That is it. We can call it I. Towards the x-axis we have some sort of vector. Just if you are familiar with the vector and so on, you'll just understand, and we can just call it z. So 0 1, that is 1 0 1. We have just created that. These we do call it basis vectors. Okay, yeah, this is the thing, right? Now basis vectors are basically some sort of vectors. Using that in the dimension we can present any value, right? So we are not going to get that deep about the basis vectors as it's not the main point, but you can easily understand that if you want to present any point in the x-axis, you can easily use this one, right? Maybe for example 100 in the x-axis, right? You can easily represent it by what? 100 1 comma 0, right? Obviously multiplication of this. And in the y-axis maybe 99. So in the y-axis it can be 99 in the y-axis can be presented by what? 99 0 comma 1, right? And if we just add this up, for example, maybe there is a vector, and in the x-axis it's 100, in the y-axis is what? Maybe 99. So you can easily use this one, like 100 into 1 comma 0 plus 99 comma 0 comma 1. That means this whatever we have or whatever value we have in this 2-dimension, we can just represent using only these two vectors. These are basically basis vectors, and now this is only for this 2-dimensional one, and depending on different dimensions it will change. So this is the user case of basis vectors, but we are not bothered about it. Then what? But here you can see these two vectors, basis vectors, are or in a way that there is a 90-degree out here. That's the point. Okay, so that's the point. That's what we are looking for here. Orthonormal vectors, you can call them orthonormal vectors. And earlier I believe we have seen using that via dot product. So if you have worked with vectors, you might have heard about dot products, okay, or cross products also. Okay, so let's just remove these parts so that doesn't bother us. Okay, just remove this part. Great. Now let's focus on this part. Okay, so you can see in orthogonal matrices we have orthonormal vectors which make up all rows and make up all columns. Okay, then this means that A transpose multiplied with A equal A into A transpose equal identity matrix. So if we have an orthogonal matrix, this is how it's going to work. If we have an orthogonal matrix which is A, this is how it will work. Now the factor is in matrix, you have to keep it in mind, that is if you have A matrix and if you have B matrix, for example this and this, A into B is never ever B into A. But for orthogonal matrices we do for example in orthogonal matrix we do have that A transpose A is equal A into A transpose. In general it doesn't happen, okay, but it's principle. Okay, this is how it does work. Now you may ask, how do we understand that? Easily, let's just go for that. How? Let's just go for that. So we do know right now that we have two basis vectors which are 1 0 0 1, isn't it? Right. Okay, 1 0 0 1, and if we can just form vectors we're using that, right? 1 0 0 1 x, these are like our x vector 1 0 for the x-axis as a whole, right? This is our I vector, and the y-axis that's the thing. So we can just create a matrix using that. Here is a make up all rows, or when the orthonormal vectors make up all the rows, make up all the columns. So using that, if you just create the row and column, you can just easily get that. So it's just, it doesn't matter how you form this one. So you just form 1 0 0 1. Okay, so you just have the vector, so you just form that 1 0 0 1. Now you can ask how we are understanding these things. So if it's represented just like the x and y, so you can easily understand in the, okay, let me make it clear so that you understand it better, because I believe there is a confusion with that. Okay, let's create black one. Okay, this is a matrix. We are just creating that using that. So let's keep all the x values in this direction, all the x. Okay, let's keep all the y values here. So here you can see x, right, is x value in this vector. Isn't this the x value? Isn't this the y value? Right, isn't this? You can see, what does it mean? 1 0. We have 1 unit here, we have 1 unit here. What does it mean 1 0? It means here we have 1 unit of x but 0 unit of y. That's it, isn't it? Yes, that means, so this one is x and this 0 is what? Y. Talking about this thing, what does it mean? 0 1. It means we have 0 which is we have 0 contribution from obviously x, but we have 1 unit from y. So x as a whole should be 0 1 1, isn't it? So using the basis vectors, we are just representing, we have just created a matrix using 2 basis vectors. Now interestingly, we can call this, for example, we can just call here this as a matrix. Great. If we now have the transpose of A, you can easily understand this row should be the this column should be a row, and if we just form that 1 0 1 0 and we have 0 1 as a column, we should make it a row 0 1, right? They are exactly the same, right? And now, do you remember if we multiply, and you can easily see these are, isn't this an identity matrix? Isn't this an identity matrix? Yes, obviously these are I2. They both are I2, right? And you also remember, if we multiply anything, any vector or matrix with identity matrix, we just end up with the same thing. So they both are the same. Just assume that for the sake of this practice, just assume this A is an identity matrix, okay, and this AT is some sort of matrix, normal matrix, okay. So if this is identity matrix, identity into AT should end up with what? AT, right? Something like that. And then AT is again an identity matrix, so it should end up with I. So just like that. Okay, I just this is not a good example or explanation. I'm just meaning that, okay, whatever you multiply, and obviously these are all, both of these are our identity matrix. So if you just multiply, we'll just end up with I2. Okay, so this is what is mentioned. This is it is written as I because it's just meaning, okay, whatever the dimension is, it should just consider just like that. So you can just call it I, no problem with that. So that's the thing. So now, can you identify which is just, if I just remove this one, can you identify which is AT and which is, or A transpose on A, not A transpose? You can't. That is why, one of the reasons, if you just multiply them in the obviously A transpose and then A, or A into A transpose, it just ends up with I. There is no problem with that. But for other cases, other matrices which is not identity matrix, there is some problem. Okay, in this case we use basis vectors, but in real life there might be some cases, but in general it's basically the basis vectors which are orthogonal matrix. Otherwise it's not that easy to form one. Okay, that's great. Which also means this one. Now if you just look into this, that means A transpose equal I obviously identity matrix. Then we just add an A inverse in the both of the side. Obviously, if you just add A inverse in both of the sides, then these two just go on, and then AT equal A inverse I, right? So yeah, so that means that's interesting. That means if that's the matrix which is orthogonal, if you want to get the inverse of a matrix and which is orthogonal matrix, if you just get the transpose, it's the actually is the inverse matrix. Okay, that's an interesting one. But in real life, if it is not an orthogonal matrix, it's never going to happen. There are lots of rules to get an A reverse. Okay, a reverse matrix. Okay, but orthogonal matrix has some benefit. If you can get one, you can easily get the reverse matrix, and which will be basically the transpose of the matrix easily. Great. These are the things you, I believe, yeah, you should keep them in mind. Okay, now this is your exercise. Okay, this is a problem, so feel free to pause this one and you just try to solve the problem. Here you can see, use the dot product to demonstrate that any two columns of I3, this is our I3 identity matrix, which we have 3 rows, 3 columns. Okay, any two columns, if you just use dot product, you will get basically you can easily mention that he has they are orthogonal matrix. Now how can we say that? Let me just give you a clue. The clue was when we had these two basis vectors 1 0 and 0 1, and what, let me just write it here. Okay, if we have 1 0 and 0 1, if we just do the dot product, how do we do the dot product? Right, so you see, we do 1 into 0 plus 0 into 1, which we end up with 0, which is the dot product, and it's 0. When we find out the dot product is 0, we can say there is a 90-degree difference between these two vectors, which is 1 0 and 0 1. This is exactly what you have to do. That's it. So you can just practice with it, no problem with that. And if you just practice with these two and then repeat this and follow for this matrix K, which is our another matrix. Okay, great, that's the problem. And now let's move for this one. So in real life, we have been learning this matrix stuffs and so on, right, for now, by now. So in real life, when we are going to deal with machine learning models, there will be lots of data. Okay, so and obviously as we have lots of data or dimensions and so on, so it's going to be tough to work with them. So we need to reduce the dimensions, we need to rank results, we need to recommend something. Like for example, sometimes you use Netflix and they do recommend based on your liked movies or watched movies and so on, right? And in NLP or in natural language processing, like for example, if you have been if you have heard about LLM, which is large language models, like the chat GPTs and so on, basically NLP, if you just learn about NLP, then you will end up with LLM. Okay, basically same format. Natural language processing, start with NLP and then you end up with large language models. Yeah, dealing with the language models. So here, there as well, we use the SVD. Now, what is SVD? Singular value decomposition. Okay, this singular value decomposition and eigenvectors and principal component analysis (PCA), all of these uses matrices. These formats like eigenvalues, vectors, or matrices, and so on, inverse, and a lot of stuffs. So that is one of the reasons we have been learning matrices for a while. And again, you will have these as the exercise 2. Okay, apply the identity matrix I3 to the vector U. Okay, this is U. So apply the identity. Apply the identity means multiply. Okay, multiply. So I'm just asking for I3 U. Okay, what's that? Apply the matrix B to the vector U. So I'm asking for BU. Okay, and then concatenate vector U with vector U2. Okay, it was U. Okay, yeah, to form a matrix U. That means U equal what? U plus U2. Okay, just need to add them up and then apply the matrix B to the matrix U. Okay, yeah, that's the process. I've been provided the value and that's it. Now let's go for another concept which is very important here, and this should this is what we will cover to end our session. Okay, that is eigenvectors. Here you can see there is two pictures of monoliths. Obviously this is the main one, obviously, and here you can see, just assume that in real life also, if we check an image and so on, in digital image and so on, like in digital image especially, every block there is a huge number of blocks, lots of blocks out there in an image, and each block has some sort of value assigned to it. depending on the value, basically they are called pixels. Okay, like these ones, sorry, this square. I just gone through square. Okay, this whole square is basically a pixel. Okay, so this, it has been assigned some value in digital world. As the Mona Lisa picture is actually a real image, it was not, but like whatever you are seeing in the screen is basically there are lots of pixels, and you will see sometimes in your screen you might see some portion of the screen has been damaged and you cannot see things properly. Basically those are pixels and there is some value assigned with it, and just like that it just generates the color. Okay, so in real life, when we are going to use the machine learning models, whatever image we have been provided, we just divide that and we just try to get the pixel values for each portion in the image. Okay, so just assume that this is a Mona Lisa image, and we've just created few small pixels, and you can see, just if you just think this as a axis and this is another axis. Okay, assume that this is, there are two basis vectors, no problem with it, just assume that there are two basis vectors. Now if we just reverse the image, you see, if you just reverse the image, you can see Mona Lisa is directed towards here, this part, but right now she's directed, her eyes are here in this portion. So somehow assume that we have done that. Okay, so after that you can see that this blue vector and the red vector, basically the red vector was basically in the y-axis, right? It was in the y-axis, and after that it's still in the y-axis. The blue vector was in the x-axis, and it's still in the x-axis but minus x. Okay, this is plus x, this is plus y, this is just here. If you just look into that, it's minus y. Okay, okay, it's just minus y in this direction. Great, minus y. Okay, great. So the thing is, if we somehow just maybe some sort of matrix calculation or matrix multiplication, whatever we have just applied to these vectors, these two basis vectors, they have just changed their location from earlier to this, but still they are in the same direction they were. These two vectors are going to be called as eigenvectors. That's it. I hope you got my point. It will be clear if we just look into other examples like this. Here you see the earlier image we had. This is Mona Lisa basically looking towards this person, but somehow we have applied some sort of matrix or whatever it is, and it has moved from this to just like that. Now you see this basis vector is still in the x-axis, although it can be within minus x, no problem with that, in the minus x axis, but this vector has moved in a bit, and it was basically in the y-axis earlier, but it is not in the y-axis right now. After we moved the image, it's basically somewhere between x and y. That means this vector, we cannot call this an eigenvector. We can call only this blue one an eigenvector. Okay, after some sort of conversion, if it ends up in the same axis, is the basically this one is the eigenvector. So in this case, both of them were eigenvectors. Why? Because they ended up in the same direction, same axis, y-axis. And this, for this, it was in plus x, it ended up in minus x, no problem, but in the same dimension or same axis, no problem with that. Okay, and now let's talk about another concept which is called eigenvalue. Okay, now understand, as we have seen in the last example, that this one, once converted, it just does not remain in the y-axis. Okay, so this is our eigenvector. Now I will mention obviously why eigenvectors are important. You will see. Great. Now the question arises is, here you see we have 1 unit, 2 unit, 3, 4 and 5. It had a length of 5. Okay, after the conversion, does it have the same length? You see 1, sorry, 2, 3, 4, 5, same, it is 5. That means if it is exactly the same, then what should we have? We can call that it's exactly, like obviously if we divide them we will have 1. That means this is eigenvalue. Okay, this is the basically we can call it next, we call it before and maybe. Okay, that means before we had the value in 5 plus 5, after that we had the value in here and it's again plus 5, and if we just divide we get plus 1. That means this is the eigenvalue. It basically shows how much the vector has been stretched, zoomed in or zoomed out. That's the point, right? In our if you use any touch screen phone or tabs and so on, you can zoom in a bit or zoom in and zoom out, right? That means they there was no zoom in or zoom out. It's exactly the same, so that's why 1, no problem. But if we look into this example, here you see this one is an eigen vector, because after the conversion or after the multiplication or whatever it is, after the change, this vector did not change its dimension. It was in the x-axis and now it's in minus x, because obviously it was in x minus x, right? So that means it's eigenvector, but this is not. It was earlier in the plus y, but now it is not here, it's somewhere between. So this is an eigenvector, but again as I mentioned, but this is currently, if you just look at the 1 2 3 4 5, it's in 5 minus 5, but it was earlier in plus 5, right? 1 2 3 4 5 plus 5. So how can we understand? So we can just the next one n and b, n equal minus 5, b before 1 was plus, so it is minus 1. So this is the eigenvalue. Okay, this is how we can understand. So what's the importance of eigenvalue and so on, right? We'll understand them within a while. But before that, if you look into our matrix, let's talk about the matrix determinants. Okay, matrix determinants. So if we have any kind of matrix, this which is this one, assume that we have a b c d, whatever we have value. Determinants are basically some sort of scalar values we do get for a particular matrix. Okay, they are called determinants. How do we get it? In general, this is how it happens. We have a b c d. So what happens is, first of all we fix a. Okay, a, right? Then these values do get blocked, and you just multiply a with this value d. Great. Now there is a format which is, first of all you go with 1, then we go for a, then we go for b, right? So we're done with a, then we go for b. But the thing is, as it is the second one, we have to add a minus here as well. But for the first one we had just plus. Okay, just keep it in mind. There are some laws. There's a generalized law, but yeah, just for not getting deeper into it, you can just search for how to do matrix determinants, how to do that. You can easily understand that. I'm just trying to show. Okay, as we have selected b, now these two again gets blocked, and we just multiply with c. That's it. That is how we do it. So that's the thing. So 4 2 minus 5 3. So for the 4, just block both of the three others. So 4 into minus 3, right? Done. And the minus, as it's the second one, as it was the first, we had the plus 1, the minus, then minus 2, and it is minus basically. Oh sorry, my bad, I made a mistake. Okay, so this is 2 obviously, and that is as is the second one, so we'll add a minus here, no issues. So 2, then they are blocked, then 2 into minus 5, this is the one. So we do it. Now this is the same process which we have to follow if the matrix is a huge one. Here is the example. here is the example. Here assume that we have huge, we have how many rows? 1 2 3 4 5, and you can understand by this number 5 rows, and we have columns. How many columns? We have 5 columns. So now if you just want to find the determinant of this matrix, you have to start with first of all this one. Okay, just I'm not sure why this is getting formatted. Okay, let's just forget this one. Okay, if we just fix this one, which is x1 comma 1, which is the row 1 and column 1 value, we just fix that, then all other things gets blocked, and then we multiply that with the basically the determinant of the remaining matrix. This is how it works. Now you may ask, hey, earlier you didn't mention about the determinant value, because it was simple, so you just didn't know, or you didn't have to go for that. So earlier when we block this one, the d, basically we just had one value and we just mentioned that. But right now what we have to do, you have to just multiply these with the determinant of it. Okay, so you have to multiply this with the determinant, which has these, all of these matrix. Like this is a matrix, you have to find its determinant and then multiply this with this. Okay, only this part is done right now. Okay, then it moves on, it goes on and on. Okay, so great. Then assuming that you want to get this determinant, obviously this part's determinant, the value of the determinant here, and then it again goes for the same process. What do? You'll just if you want to multiply that, you will just for example, if you just want to get the determinant, you can just call it just like that, 1 equal to what? Then it will again follow the same process, which is x 2 comma 2. It will be multiplied again by the determinant of this. So it goes and goes on and on. So there is a lot of things, right? And now after a while, after some moment, I will just mention how we can get the determinant value using the eigenvalue or vectors. You'll see. So here you can see there are a lot of looping we have to go for, and that's the process, the ideal process. So that's why we're not bothered about it. So that's the ideal process, and we'll just go for it. And there is an example for sure, and just look for that. This is the one. It's not that difficult because it's as we have there's 3 rows and 3 columns. So it's easy because once you block this one, you have just these two, and we have this one, and it's easy, as you understand, as we have also mentioned about this. -1 will be multiplied with 1 only, because -1, once you select this 2 gets blocked, and it gets it's multiplied 1, and so on. A lot of things that happens, and we just deal with it, this one, and then that's how this one came in, -1 into 1. Great. Okay, this part, and then once you select, like as is the second one, minus is added here, and as we select 3, these 2 gets blocked, and we have 5, 3 into 5. So this is how it works. I just don't want to like show much more about how the process goes on, because it's not that much relevant to us. If you want to learn about the real process, how it is solved, you can just check any video. But the goal is, this is the process, okay, and there is nothing wrong here. If you understand it properly, that is great plus, okay. But if not, you have to look for some videos, okay. Now this is your task, which is to calculate the determinant of the matrices below, which is pretty easy, right? The last one was something like that, 3 into 3, and these two are straightforward. Now the interesting factor about the eigenvalues we have learned and the determinant. Now you see, for the huge matrices used which we will use as input and so on, we need the determinants or inverts and so on, right? And you have seen, to get the determinant value, you have to loop and loop and loop. You have to go for the now what I am mentioning is here, right? For the huge, like 5 into 5, you have to just loop for this. You have to loop for a lot of times, because this one, determinant of this, obviously this, you have to then again, as I mentioned, multiply this with the determinant of this. And then for the For this, we will multiply this with this, and so on. It goes on and on. And if you have worked with computer programming, you will know that the loop process and other, it takes obviously time. Okay, but you don't want your machine learning models and others to take time or that much of brain power, right? There is in the mathematics, obviously in mathematics, there is an easy way. Like the determinant of a particular matrix is basically the product of all the eigenvalues of X. That means a particular, as mentioned, as a particular matrix. Now we will learn about this, what is eigenvalue, what is eigenmatrix. We will learn about it much more in depth. We'll see the code part, that's very important. After the slides, I'm just going to go for that. But here you see, and the determinant of a particular matrix will be the product or the multiplication of all of the eigenvalues of that matrix. That means if you just have the eigenvalues, easily we will get the determinant. We just don't need to look for them. That's the process. And if the determinant of some matrix is 0, that means that matrix collapses space completely in at least one dimension. Okay, we'll see what happens. And if it is 1, it preserves the volume exactly, and less than 1 and greater than 1, there is a lot of things. Okay, almost we are at the end of the theoretical part before we go for the code part. Now you can see the Eisen decomposition. This is how basically, this is a format, this is how we can get the eigenvalue of a particular matrix. That's it. Okay, yeah, the matrix is singular if and only if any of its eigenvalues are 0. It's called singular. That means what is the singular format? For example, 1 2 2 4. So it's singular. Why? Because 2 4 is basically the multiplication of 1 2, isn't it? That's the thing. That's how things work. So matrix is singular if and only if any of its eigenvalues are 0. So that means when we will work with it, you will see the one of the eigenvalues of this is 0. And again, what is eigenvalue? As I mentioned earlier, that is after, is basically something like zoom in or zoom out. If a particular eigenvector has been zoomed in or zoomed out or whatever, if not done anything, then it's 0, obviously. Or okay, under specific conditions from Goodfellow's book, obviously the maximum of x, if x is largest eigenvalue. Okay, again in the real life, how this Eisen decomposition works and so on. Basically, if you want to, like for example, this is an image. Okay, this is an image. This is our image, and it has how can we call it? Okay, just like the basis vectors. Okay, like 1 0 0 1. Okay, so it's like, and now if you just create, obviously they do cover. If you just have the parallel line like that and the parallel line here, so there is some sort of square matrix. Okay, so in code we do represent these just like that, just like 1 0 and 0 1. We do represent them just like 2D matrix. If 2 into 2 matrix, basically, if this is square image, and if you want to scale this image equally in every side, theoretically the eigenvalues we will have is going to be whatever we have here. Okay, they will obviously have the same value, they will follow the same format, and they will have something. So this is the thing. I'm not going to get deep into this thing because it might be overwhelming for you, but this is something you can take a screenshot of. This is something you can come back later on when we work with the whole summer school. Okay, we'll learn about it later on. Okay, but there is another concept which is matrix type. Okay, so if the eigenvalues, if all of its eigenvalues are greater than 0, that means positive, we call the matrix as positive definite. If it is all of its eigenvalues are 0 or greater than 0, okay, it's positive semi-definite, and then negative definite and negative semi-definite. So in real world, these eigenvalues eigenvalues, what do they represent? Basically, in real world we will have data which we will have something in CSV format, and then we will just convert them to some sort of matrices. Okay, we'll convert this data, we will have lots of data. Okay, in real life we have CSV format data, convert it to some sort of matrix, and every matrix, as we have learned, we have some sort of eigenvalue or eigenvector, right? So that means that means whatever data set we are working on, that has some sort of eigenvalues related to it, right? So yeah, that's the thing. So eigenvectors as underlying characteristics of a data set. Basically, as mentioned, data sets are basically, we do have them in general in CSV formats, and then they're basically an underlying characteristic, obviously, right? Because they are basically then converted to matrix, and these matrices do have that eigenvectors, so eigenvalues. So that can be recombined into any members of the data set, and you can have eigenfaces and voice and a lot of things that happens. Even in quantum mechanics we do have that, and SVD, Moore, Penrose, and principal component analysis. We'll learn about it later on, but not in this session. So basically, because whatever we have learned today, for some it will be overwhelming. So take your time, learn these things deeply from other videos as well, or practice them up, whatever the 3 exercises I provided. Okay, so we'll just learn about it. Now we'll now go for the coding part. Okay, so I'll provide this code notebook in the description for sure. But so earlier, yesterday, or the other session, we have just covered, if you have seen, we have talked about these portions like vector transpositions and so on. So norms, L2 norms, and so on, matrix and so on. Okay, so okay, that's it. So matrix transposition, we have talked about it, and now talking about matrix multiplication, we have also talked about these as well, as a whole. Basic one, scalar multiplication, and you can see the matrix inversion. This is how we can do it. Okay, you just use this n one, okay, for the numpy. Okay, a lot of other formats, obviously, for PyTorch. This is how you do it, and let's focus on the eigen decomposition. Okay, let's see an example. Okay, this vector. Okay, what's the value of it? Okay, -1, 5, 3 array. Okay, so assume that we have a vector which is 3, 1. Okay, so if you just look into here, we have 3, that means 1, 2, 3, 3 and 1. This is the vector. Okay, great. We're just watching that in a light blue color shape. Okay, no problem. Now what happens is applying a matrix to a vector. Now this is a vector, so if we apply a matrix to the vector, it can be rotated, or it can have any single format, can linearly transform the vector, rotate it or rescale it, or whatever, it can happen. The identity matrix introduced earlier is the exception that proves the rule. Applying an identity matrix does not transform the vector. That's the exceptional case. That means if you have an identity matrix, it does not change whatever you add or whatever you multiply with the matrix. Okay, so that's the point, but that's a different case. But we can just see this just like that. You see 1, 0, 0, and what does it mean? So I believe I have to show the write it down here as well. Okay, so that you understand. Take my time. So 1, 0, 0, 1 easy is the identity matrix, right? Isn't it? 1, 0, 0, 1, right? So yeah, that's what we're talking. Okay, so assume there's a, you see 1, 0, 0, 1, and now IV. What does it mean? That means multiplied with something. IV, that means we have multiplied the identity matrix with V, which is another vector, which I mentioned, maybe 3, 1, right? So easily 3, 1. As mentioned, identity matrix, if you multiply that with the the vector, it basically ends up with the same thing. So what I'm trying to mention just we have seen the vector in the code, right? 3 1, 3 1, right? 3 1, yeah. If now we multiply this vector with identity matrix, it actually does not change. It remains in the same position. That's what we're looking into. Okay, so IV is basically, that's it. You can see after multiplication it's still 3 1, right? That means if you just want to check if they are the same value, and they mention yes, true, they're the same value, and you see the IV, if you want to look for that, it actually and we want to see that in the blue color, not the light blue. You can see it's exactly 3 1. So we have multiplied this. IV actually means we have multiplied I with V. Still it has not changed this position, because as mentioned, it's the identity matrix. Whatever you multiply with it, it does not change. But in real life, the matrix we multiply is not actually identity matrix in general. We do have lots of other things. So assume that if you have a matrix which is this one, 1 0 0 minus 1. Okay, if you multiply that with our 3 1 vector, now we have 3 minus 1. Interesting, right? Let me just mention this again. What we are doing is we have this 3 1 vector, and we thought like, okay, let's just multiply this vector with a matrix which is not obviously the identity for now. We're done with the identity. Now second one, maybe 1 0 0 minus 1. I'm not sure about it, but yeah, let's look for that. 0 1, yeah, great. So now you see the vector, or now the vector we do have is or the matrix we do have. We can also call this a matrix because it's like just it has just 1 row and 2 columns. That's it, but no problem with that. 3 minus 1, no problem. Now if you just plot them and want to see the difference, you can see easily. You see, this was the earlier one, 3 1, but once we multiplied the matrix, this one, with this vector 1 0 0, this is the matrix with this V. If we multiply that and we get EV, this now the new vector actually went here, the EV. This is the EV. Okay, so let me just make it clear. This is V and this is EV, and this is our E. Okay, we had V equal 3 comma 1. So after multiplication, or after multiplication of the matrix with the vector, you got something which has changed its location, right? Great. Okay, or the matrix F now, rather than E, if you just multiply with this one, minus 1 0 0 1, multiply F with V, you will see something like that. Earlier this was here, but now it is here. So right now you can see this is something like mirror, right? Just like the mirror, this is the mirror, and you are here, and maybe you can see your reflection out here. So just like that. So it totally depends on the matrix we do multiply with some sort of thing, right? It's totally getting different. So that is basically called affine transformation. The scaling, sharing, rotation, whatever we do have, if we just multiply them, it's basically called affine transformation. Okay, great. You can learn more about it from this blog. Okay, provide this notebook link, so you can just go for that. Again, assume if you have this matrix minus 1 4 2 minus 2. Okay, if you multiply that with our V, we'll have 1 4. That's totally different thing, because the V, our V vector was 3 1, right? So just check, let's check the image. So this time the V was here 3 1, but after multiplication with A, it is here, the new one is here. No problem. Okay, it can happen, for sure it can happen. V2, now assume if we have V2, another one, which is 2 1. V2, if you just look for 2 1, right? 2 1, this is 2 1. If we multiply A with V2, we end up with this one. So it again changed. Okay, it can happen. I'm just showing you okay how we multiply and the value does change or so on. Okay, again, now talking about v, we also know by now our v is basically 3 1 vector. Okay, if we use the transpose of it, obviously the 3 1 is in the row format, and now it will have in the 3 1 which will be in the column format. Okay, we can do that, but there is a change. You see, the vector is called an array because you see we had just one bracket out here, but once we use the use matrix, we use, obviously we had converted it to matrix and then use the transpose, and now you can see it's in the matrix format, and this is a whole column now. Earlier it was 3 1, now it is 3 1 as a row, now it is 3 1 as a column. Okay, it can happen for sure. There is v3 v4 much more. So basically we have v2 again, right? V2 here, v2. So using all of these and using transpose, whatever, we can create a matrix. Just that is not an important factor. We just assume that you have created a matrix which have these values. Okay, and earlier these values were actually part of 4 individual vectors, and currently we have a matrix, right? This matrix 3 2 minus 3 minus 1, let me just write. Okay, 3 2 minus 3 minus 1, sorry, and 1 1 minus 1 1, 1 1 minus 1 1. Okay, great. So we have just created this matrix, for example maybe x, and while doing that we just use 3 1 2 1 this and a lot. This 3 was initially like a v had 3 1, but we have just took the transpose of it, which is 3 1, and we just used it here in the matrix. We can do that. Okay, now we are calling this as v, big B, v. Okay, so I can just do it here, v. Okay, now here we are saying if you multiply this with I, you just end up with the same thing. Obviously we know that, right, at the matrix. But if we multiply this v with A, which we had somewhere earlier, which is this one, I believe, yeah, this one, this some sort of matrix, we get a different kind of stuff. Okay, get a different kind of value, different thing, something like that. Again, this is AV. Okay, AV multiplied A matrix with the new matrix we have. So this is V, and we have some sort of A matrix which we have something. Okay, great. Keep it in mind, this V was actually created using some individual vectors. Like 3 1 was converted to basically was transposed and was part of the matrix. Okay, so basically vectorify, if you use v comma 0, what it means is, if you just look into this v, sorry, this v, this 3 1 as mentioned, this is basically the transpose you see here, matrix v dot transpose, that means it was transposed basically. So actually what was the real vector, if you just want to see for the first column, it is, this is how we write the code, and you'll see 3 1, this was the actual value, actual 3, right? Okay, great. Now why are we bothered about it? We are bothered because now we have as mentioned, we have four vectors, right? We had 4 vectors actually. Initially we have v, v2, v3 before, right? These 4, if we just plot them, and we do refer them by these things, vector 5 v0, it means v, this one means v2, this is v3 and v4, no problem. But this is the part that we are bothered about. That is basically if you multiply Okay, okay, 3 1 2 1 3 minus 1 minus 1, they obviously they will be there in the plane, but this whole thing, if we multiply with a and then try to see like where was the change for that vectors, particular vectors, especially talking about for the AV, right? Especially for this 3 1, where did it go, where did this one go, where did this portion go, and so on, how was they impacted? You will see obviously the format is same, and this actually means, okay, the new change for this vector, this one, earlier it was here and now it is here. So you see, this is how it works. This was our 3 1. Once we use a with it, it converts to here. This was our what, another one, obviously not sure though, 3 1, maybe 2 1, okay, 2 1 and 2 1, yeah, and then it converted to this. So the whole goal is that these, like every time we won't like use a single vector and try to look for how the new vector looks like, but you understand that these single vectors actually form a big matrix, right? Now if we multiply something with this, things do change, right? This is how it ever changed. This light blue changed to this green changed to this dark green, okay, and a lot of other stuffs, right? Yellow changed to red one, and the white to ash, right? This kind of thing. So earlier we had only this particular one. So let me just take this. Okay, let me take this one and make you understand. Okay, great. Let me just zoom in a bit. Okay, this is our V. This is V2. If not sure, I'm not sure though, it should be 4 maybe. Let me just check. Light blue, light green, orange. Okay, orange the V4. Okay, let me just see from here as well, and let me just refer 3 1, right? It was transposed, right? So initially it was actually this 3 1 is basically 3 1 in general. This is our V, and V2 was actually 2 1, and V3 was actually, I believe, -3 -1 if it is -3. V4 was -1 1. Let me just check it again. V3, where is that? This is not something like very serious or fierce or tough kind of stuff. It's just simple. I'm just taking my time. Okay, -3 -1. Okay, great. Okay, V3 is -3, right? Okay, so it should be V3. So it's our V3 and it's V4. Now see, and using the V transpose, V2 transpose, V3 transpose, V4 transpose, just created a matrix, and we multiplied a matrix with it. After that, these ones, obviously this is part of a matrix, we just don't need to bother about it, but they were impacted, and this blue one was here earlier, the VB. Now this is our AV, and this is our AV2. This is our AV3, and this is our AV4. So this is how it impacts, this is how it changes in the real world, in the world when we solve the problem. Okay, now talking about the eigenvectors and eigenvalues, as mentioned, we have seen that earlier, right? Okay, so eigenvectors are basically the spatial vector V. So we are assuming this V is an eigenvector, and we multiply some sort of matrix with it, assuming that this is the eigenvector, and if we multiply some sort of matrix with it, it converts to a multiplication of eigenvalue. This lambda is an eigenvalue, and this is the eigenvector. Okay, this is the concept. Okay, so this is how I believe this. I haven't showed these things in the slides or here previously, so let me just write it here again. A is a matrix which, assuming V is a eigenvector, we don't know, in general it can happen, assume that this is eigenvector, that is 3 1, assume that. So if we multiply a matrix with V, we will surely have an eigenvalue multiplied with V. We'll have something like that, and this eigenvalue is something like lambda. This is how we get it. And you know what is eigenvalue, right? Isn't it? Is a scaling, like zoom in, zoom out, right? We have mentioned that earlier. And this is a vector, eigenvector. What is eigenvector? As mentioned, you have seen it earlier as well. If we just maybe we had this x like 0 1 1 0 and monolithous image, right? You see, then we have made some changes, and basically the changes are made by multiplicating any matrix with it. Okay, maybe they have changed, now it has changed to this, so we called that this is the eigenvector. This is not, because it is in x-axis and y-axis. So in the y-axis it just moved from here, and it is still in the x-axis. That's it. So that's the concept. Simply it will take your time, it will take some time, and you should also take some time. Okay, so just now assume that A is this our matrix -1 4 2 -2, no problem with that. And there is a way, there is basically called the QR algorithm. Using QR decomposition, there is obviously I will share this a video. It's not obviously mine. I will share some videos in the description section or comment section. You can just check them out. So using one of the methods with QR algorithm, we can actually easily get the eigenvalue and eigenvector. That's it. Because right now we're not focusing on the math, rather how that comes about, how it helps. That's it. So for a particular matrix, okay, using QR algorithm or decomposition, we can easily get its eigenvalue and eigenvector. Assuming A, okay, just check this out. As mentioned, A is a matrix. We are talking about A is a matrix, and we are saying that if a matrix is multiplied with an eigenvector, we end up with eigenvalue multiplied with eigenvector. Okay, these we are our eigenvector. This lambda is our eigenvalue. Great. Okay, there is a way. This is the shortcut. So what we can do, we can easily get the lambda, which is our eigenvalue, and the v, which is our eigenvector. We can easily get through this np numpy dot len l dot eig. Then the matrix we do pass. So a matrix. So a matrix is eigenvector. This is the eigenvector we do have. This is our eigenvector. And you may say, hey, this seems something like matrix. Actually everything is a matrix, right? Even talking about the vector, that's also. But yeah, that's the thing. So this is our eigenvector, and the lambda, this is our value in the lambda. So here you see in the matrix format, here obviously we have here two eigenvectors. Within the matrix we have like two. This one is one and this one is another, right? These two are our two eigenvectors. Okay, again, as we have two eigenvectors, we also have for this particular eigenvector, we have an eigenvalue. Like how? So what is the eigenvalue refers to? So if you just look into this image, what does it refer to? You will understand. For example, it was v, right? Okay, after that, if you multiplied a with it, av, now if you just compare them, you have to mention how much this v has stretched. To be honest, you can see that these are not eigenvalue or eigenvector, whatever it is. It is not directly. We have just multiplied them. I'm just checking the position. That's it. These are not actually, to be honest. the eigenvalue or eigenvectors. In real life, what would have happened is, I believe, no example directly to that. This is exactly not opposite, I believe. It does not seem to be. So it is not exactly. But if we had, as mentioned, if we had V here, and if we would have multiplied or applied a matrix with it, sorry, this is V, and we just use or multiply a with V, we might have ended up with AB. Okay, so then we would have tried to look for, okay, how much has is stretched, so AB by the length of this, and we might have seen 2x or whatever, 2, sorry. So this should be our eigen value. Okay, this should be our eigen value. So that is exactly what it is. So the vector has been stretched 1.37 x or whatever you call it. Okay, and this vector has been like this, stretched and in the minus version. Okay. Okay, so how can we understand that? How can we see that? We'll see. So as I mentioned, this is our eigenvector. This is one eigenvector. This is our another eigenvector. So we've just divided. We're just trying to see, okay, for this particular vector, where was this earlier, and what is its eigenvalue? We have easily found out, and you just don't need to do it. You can easily understand from here as well. This is the eigenvector, this is another eigenvector, and this, for this vector, this is our eigenvalue, and for this eigenvector, this is our eigenvalue. Okay, great. So for the first one, we're just trying to look for how it worked. Okay, you see, this is our V. Okay, this is the first eigenvector. This is its eigenvalue, and we want to see how it was impacted by multiplying A with the V, with this V, this small v, and we got something, some sort of value. And then as we know, AV is the matrix with its eigenvector, is basically the, what I would call, the eigenvalue multiplied with its eigen vector. So you can see exactly the same. That means they verify. That this is for the verify purpose. Okay, that's the verify. That's it. But what's our goal? The goal is to check V and AV, to be honest, to see if they are in the same direction and V has been multiplied 1.37x or not. That is the goal. If you just look here, yes, that's it. This is our V. Let me just give you, and I believe after this it should be just an easy concept for you. Okay, right? Why? You see, this portion is basically our V, and this portion is our AV. That's it. There is a trick to get, like, we had this. So let me just give you the summary again. We had some sort of matrix. Using some sort of QR algorithm, we just tried to find out, hey, tell me what kind of eigen vectors I can have for this matrix. It easily mentioned you can have two eigen vectors. Okay, now you can say it just returned us in a format of a matrix. Now you can see it easily from here. Here you can see we have two, right? This one is one eigenvector, this one is another eigenvector. Okay, then we just okay, no problem with that, we are happy with that, no problem. Then we are saying, like, okay, as we know, that's good, and what should be this one's eigenvalue? This one's eigenvalue. What should be this one's eigenvalue? Which we can consider as a lambda 1. Oh, and what should be this one's eigenvalue, right? We can just, right? So yeah, I believe you understood the process. That yeah, once this vector, actually we can easily get these eigenvector, but sometimes it will be provided, sometimes it won't be. But actually, if the vector V was provided, and if we had the obviously mentioned A, if we would have multiplied, this is how it would have changed its direction. it would have been in the same place. Obviously the direction, it was in this axis, assuming that maybe some sort of axis, m axis, assume that, and minus it is in the same axis, right? After the transformation it was in the v, this is our v, and after transformation it's still in the m axis plus m, and it has been scaled, right? And how much it has scaled? It is basically 1.37x v, right? Obviously v is basically scaled at 1.37 into v, right? This is what it is, and this is the lambda 1 we got. This is the lambda 1 we got, right? So I believe, you see, this is the lambdas we have 2. Obviously this was for the that particular vector, and if we want to see for this one, obviously it will be like that. Okay, this is how we should do it. So it's done, right? So now if you just want to look for the second one, and both obviously at the same time, so this is how it looks like that. So this is our the first vector, it is scaled to here, so it is something like that, and it was our the second vector, and it's scaled to like that. It's in the reverse order, but it has scaled 4x obviously. And how do you understand that? Let me just look into again, show you from here, sorry, yeah, from here. You see, for this vector it was easily mentioned it will scale 1.37x. Obviously you can call it 1.3722, right? You can easily understand 1.3x, 7x. For this vector it is mentioned -4, that means it will be in the opposite direction, it will move to the opposite direction, and it is 4.3, that means scales. Okay, that is it. So you can easily understand from a particular matrix that what will happen to its eigenvector and so on. Now the point is, why are we bothered about it, right? Why are we bothered about it, right? That's the point. So we can also look for the determinants and so on. You can just look for that, generalizing determinants, how can to solve it. And the point that why we are bothered about is mentioned here. Why? You see, this is our x. Now why did we find the x here? Assume that this is a matrix, okay, which has 1 2 4 in the first row, 2 minus 1 3 second row, 0 5 1 in the third row. Here you see this is the format. Great. We can easily get its determinant using this numpy's format, np.linelg.det. Then this you can easily, this is the determinant value. That is basically what we get through looping in general. Okay, this is how we can do it in looping. Obviously NumPy does it in different format, but yeah, in general if you want to look for that, you just follow the format. But there is another way. Easily, if you want to do it manually or easy process or do it very fast, there is easy way. That is, we mentioned that here. That the determinant of a particular matrix should be the product of all eigenvalues of x. That's interesting. That means, and now if you come up here and you say, let me just give me the eigenvalues of this matrix, you'll see these are the eigen values of the x matrix we have mentioned here. Now if you just get the product or multiplication of all of these numbers, you will actually end up with the determinant. You see how to do that. You see this is the like lambdas have all of these values, and if you just use the prod for product, you will see we have this. That's it, easy. Now using the eigenvector, eigenvalue, you can easily understand this as well. So now this is not why we are just looking for that. In real life we will have huge big arrays. It's better, or the goal is to get or solve the arrays or matrix multiplication and so on and everything very fast. So we are currently basically learning various ways to solve the problem easily, faster. So basically the goal is in machine learning model, we are not computing, right? The computer is computing. Our goal is to make it efficient, make it faster, so that the computer can do it, right? So this is a faster way to get the determinant, right? Isn't it? Okay, so there are other things you can also look into. Okay, so yeah, I believe now you can just check this out, check the whole notebook and take your time and solve the issues. And yeah, that is obviously taken from, this is not my notebook, so you can just check this notebook, and yeah, feel free to give it a star to the notebook, to the real repository. Okay, so yeah, thank you so much, and if you have any questions, feel free to ask in the comment section, and obviously in our Discord survey as well. So yeah, thank you so much, and hope to see you in the next video.